Hey everybody, welcome to lesson 3 in chapter 6. Today we are going to look at thermal energy. So another kind of energy. We've talked about work, we've talked about power, we've talked about potential energy, we've talked about kinetic energy. Now we're going to look at thermal energy, which is all about heat. And this is really a special kind of kinetic energy. It's the energy stored in moving molecules. So you probably know that there are gas molecules racing around you wherever you're sitting right now. Those gas molecules, we would really say if they're racing around, they've got some kinetic energy. But what we do is we look at the kinetic energy of molecules in substances, gases, liquids typically, even solids, and we talk about them as heat. We think about them as things like temperature or heat energy. So it really is sort of a modification on kinetic energy that we saw last day. The first thing I'd like to go over is temperature, which is the average speed or the average energy of the molecules in a sample. So average, remember, means that some molecules will be going faster or have more energy. Some molecules will be going slower or have less energy. But on average, temperature is telling you what the overall energy of the molecules in a sample is. And then we end up seeing units of like Celsius or Fahrenheit if you're an American or something like that. But it really is a type of energy measurement. There are two scales that we work with in Canada and most of the world. And those scales are Celsius, which we're used to, and Kelvin. We actually don't work in degrees Fahrenheit. Again, that's an American thing, and there's something like 3 or 4 other countries in the entire planet that use Fahrenheit. We're not going to look at that because the conversions between them both are terrible. What we have here is I'm going to make a note as to some sort of token temperatures that we're used to with Celsius, and then we'll compare them to what they are in Kelvin as well. So we've got water freezing, room temperature. It's kind of hard to see where these line up. Water boiling. LN2 is liquid nitrogen, which is really, really cold. Absolute zero is kind of cool. Absolute zero is a special case, more of a theoretical case than anything, where molecules have no kinetic energy at all. They actually have no speed. So there is a bottom end for temperature, and that's where like your gas molecules, actually if they have no kinetic energy at all, then that gas would have turned into a liquid, and the liquid would have turned into a solid. So at absolute zero, there is no such thing as gas or liquid. It would only be solids. And the molecules, they don't move at all. It's like crazy, crazy cold. What happened with these two temperature scales is the one we're used to is Celsius. So if I go and I put those numbers in, we put 0 degrees Celsius in kind of a random spot. I'm assuming it's Dr. Celsius. Decided to put 0 degrees at the temperature at which water freezes. And then we measure up and down from there. So room temperature is about 20 degrees Celsius. Water boils at about 100 degrees Celsius. Liquid nitrogen, it's the stuff you've ever had warts burned off at the doctor. That's 196 degrees below zero. And then absolute zero is negative 273 degrees Celsius. That's as cold as you can get. There is no upper end. I should mention that. Temperature just keeps getting higher and higher and higher. There's no maximum. So that's what Celsius did, is they put 0 right there, which is kind of weird. And then they worked out in both directions, or he worked out in both directions. Now, Kelvin came along and did what I think is maybe a little bit smarter. We're just not used to these numbers. But Kelvin said, why are we putting 0 at water freezing? Why don't we put 0 at absolute zero and then work up from there? And he did that. He said, let's call absolute zero 0, and then you work up from there. So liquid nitrogen would be 77. Water freezes at 273 Kelvin. Room temperature 293. Water boiling at 373. What you might notice about these scales, if you look in here, that's a difference of 20 degrees. So the change in temperature was 20 degrees Celsius. And if you look right here, from 273 to 293, the change is 20 Kelvin. So the cool thing here is that 1 degree Celsius is equal to 1 Kelvin. It's not like degrees Fahrenheit, where a degree Fahrenheit is actually smaller than a degree Celsius. There's like some fraction involved. Here, one Kelvin is 1 degree Celsius. So it makes the conversion super easy. You can use this equation right down here. It turns out through this lesson and through your homework, you actually won't care whether things are in Celsius or Kelvin, because we're always going to find the change in temperature, and the change will always be the same. And again, what I mean by that is the change here is 20 degrees, and the change here is 20 degrees. So when we're finding the change in something, it actually doesn't matter what the units are, because the number is what we're after. So that's good news about temperature. There you go. Now, heat is all about changing the amount of stored energy in a sample, and it's going to be measured in joules. So the equation for heat, in fact, when you write this down, don't worry about writing the Q, because in Physics 11, we're not going to worry about the Q. The equation looks like this. I'm actually just going to write it like this, EH. I'm not going to call it delta EH, just to make life easy. We typically shorten it down to look like EH. Maybe I won't say that. Here's the working one, equals MC delta T. So that's our equation for heat energy, right? We've seen P for potential, K for kinetic. Now it's H for heat energy. Here's what the bits and pieces are in this equation. M, mass. And remember, we're physicists. That has to be measured in kilograms. Delta T. This a capital T, you might look and go, oh, I've seen that before, that's period. Well, in this case, it's actually change in temperature. So that's temperature. And the cool thing here, I just mentioned it on the last page, you can be working in Celsius or Kelvin. It doesn't matter, because you're finding the change in it, so the units don't really matter. And then there's this little C. That is something called the specific heat. And if you need the specific heat of a sample, I'll throw this out there before I forget, it's in my brain. The specific heats of different materials are listed in the homework booklet. I think towards the back page. Yeah, so here's the last page of the homework booklet, which you can find in the All Resources folder. And there is a table of specific heats. When you're going through any questions in the homework, if you need one of those values, you can go and look it up in that table. What the specific heat tells you is it's the amount of energy required to heat, I'll just say needed, to heat the material. So that's what it is. Some materials heat up quicker than others. So things like metal, typically kinds of metal heat up quite quickly. So they would have lower specific heat values. It takes less energy to heat them up. And then some things like water. Water is actually really, really hard to heat up. The bonds in water are strong, and to break those bonds and get the molecules moving, it takes a lot of energy. So it's got a very big specific heat. And if we go and look at that table in the homework booklet, you can see that some of these kinds of metal, like where's lead? Lead, if you know anything about it, it melts really quickly. So it's got a very low specific heat. It's only 130. But look at water. 4,180 joules to heat up 1 kilogram by 1 degree Celsius. So I'll put the units in there. You don't have to sweat these units too much, because you could always just go look them up in that table. But the units are joules per kilogram degree Celsius, or sometimes you'll see kilograms times Kelvin. But that tells you how many joules it takes to heat up 1 kilogram by 1 degree Celsius. And we're going to use a couple of examples today. We're going to use water. So its specific heat was 4,180 joules per kilogram degree Celsius. And the other one that we're going to use is aluminium for the Brits. It is 903. So it heats up much faster, more than 4 times faster than water, because it's 4 times less energy to heat it up. Joules per kilogram degrees Celsius. So let me show you a couple of examples using this equation. I don't think you'll find it too bad. So here we're looking for how much heat, or how much heat energy, you can think that. How much heat energy is required if we want to heat up 430 grams of water from 22 degrees Celsius to 58 degrees Celsius. So maybe you're trying to reheat a cup of coffee or a hot chocolate or something like that. We are simply going to use the equation that we wrote down on the last page. We're solving for heat energy on the left, which is kind of nice. Remember, M is mass measured in kilograms. And here it's in grams, not to be tricky, but because if you had a cup of coffee or water that you were wanting to heat up, you've got less than a kilogram, so you're probably not going to use the units of kilograms. You might go chemistry style here. So that's going to be 0.430. We are looking at water. We just wrote down that specific heat as 4,180. Very hard to heat it up. Takes a while to boil water on the stove, right? And then delta T is your change in temperature. Remember, that's final minus initial. Just to avoid the mental math, I'm going to say, hey, that's 58 minus 22. And you go and you type all those numbers in your calculator. Pretty straightforward stuff. There. Looks like we're going to need some scientific notation. 6.47 times 10 to the 4. Times 10 to the 4. J for joules. There's how much energy it would take to heat up that water. And that is a lot of joules, right? That's why it takes a few minutes in either the microwave or on the stove to heat up samples of water. Okay, so taking that heat energy equation and upping the ante a little bit, I want to look at the second law of thermodynamics, which says that heat always goes from hot things to cold things. And I think you know this, right? That if you take 2 samples, one that's warm and one that's cold, and you mix them together, they are going to hit some equilibrium temperature. There's a nice chemistry term for the chemists in the room. They're going to hit some temperature in the middle, but the hot sample is going to give up some energy. And that energy doesn't just disappear, like we said last video. Energy simply goes from one thing to another. So hot objects will simply give up their energy to the colder objects, and that happens until the 2 of them hit the same temperature. That sort of equilibrium or somewhere in the middle of the road temperature. So these I like to call mixing questions, and maybe we can even add that in here. These are a little bit more work, but I'll walk you through. They're really not bad. There's lots of calculator work. So let's look at some mixing questions here. So here we want to find the final temperature, and feel free to trim this down for yourself and just call that like TF. Find the final temperature if 240 grams of 20 degrees Celsius water is mixed with 450 grams of 40 degrees Celsius water. So here's how we're going to set up these mixing questions. We're going to do this. We're going to say that the energy lost by one sample is going to be equal to the energy gained by the other. Because remember, the hot thing is going to give up its energy, and the cold thing is going to accept that energy until they meet somewhere in the middle. So when we set up the equation like this, the sample that's losing energy is going to be the hot side, right? It's giving up some of its energy. And the sample that's gaining energy or taking it and saying, oh, thank you, that's going to be the side that started out cold. And what we're going to do here is we're going to set these up as heat energy, so mc delta T equals mc delta T. The only thing we have to remember is on that lost side, because that sample is losing energy, we have to put a negative. So that side is going to lose energy, and then the cold side is going to gain some energy. Now let's go and watch our masses and get our units all tidied up, and we're going to plug some numbers into this equation. The hot water is this information right here. 450 grams of 40 degrees Celsius water. That was the hotter stuff. So we've got negative 0.45, make sure that's in kilograms, times water, specific heat is 4180, times delta T. Remember, delta T is final minus initial. Keep that in mind. TF minus TI. Now, I don't know what the final temperature is, but I do know the initial temperature of that warm stuff was 40 degrees. And we're going to set that equal to the cold side. There was 240 grams of water at 20 degrees Celsius. So that's 0.24. This side's positive. Times 4180. Times delta T. I don't know what the final temperature is. It's going to be the same for both. I do know that this sample, it was colder though. It started at 20. Now what some of you might be recognizing here is that because we're mixing the same material, we've got this 4,180 on both sides of the equation. And like we said in the previous lesson when we looked at conservation of energy, if you had the same mass in every term in an equation, you could cancel it out. Well, here we've got different masses, but the same specific heat. So if you'd like, if you're mixing two things together that are the same, you can actually take those out. And let's do that. It makes it a little bit easier. Now what we're going to do from here, algebraically, is we're going to distribute these masses into the brackets. So I'm going to grab my calculator and do that. Actually, to save time, I'll pause the video and just show what that looks like in the end. Okay, so there's what the numbers look like after distributing. Do be a little bit careful on that left-hand side that when that negative 0.45 multiplied by the negative 40, we ended up with a positive 18. So watch that. Now, algebraically, what you're going to want to do is get all of your TFs on one side. I've got this negative 0.45 TF, so I'm going to add 0.45 TF to both sides. And just because I'm running out of space, let's go ahead and, if I'm putting all my TFs on the right-hand side, I'm going to want all my numbers over on the other side, so I'm going to add 4.8 to both sides. That's going to cancel. That's going to cancel. We're left with 4.8 plus 18, 22.8 equals, what's that, 0.456.69 TF, and divide both sides by 0.69. Looks like 33.0 degrees Celsius. So there's your final temperature. A little bit busy with the math, right? I do recommend, though, that when you go to solve for your final temperature, remember that if we started with 20 and 40, we have to meet somewhere in between those two numbers. Those are like our goalposts, and we have to be somewhere in the middle. You might be wondering, well, Mr. Heinrich, why didn't it just come out at 30? If you mix water at 20 with water at 40, can't you just split the difference and take 30? And the answer is no, because we had more of the warm stuff and a smaller mass of the cold stuff. So it wasn't actually quite in the middle. Let's try one more together quickly. It's mainly the setup that I'm concerned about, to be honest, and then it's a bunch of number crunching after that. So let's try one more. Let's try this one. Find the final temperature if 420 grams of 85 degrees Celsius aluminum is dropped into 200 grams of 15 degrees Celsius water. So energy lost equals energy gained. Now we've got different materials this time. I always like to go and tell myself which material is going to go on which side. That way I don't sort of Frankenstein the question and get numbers all mixed up on different sides. So remember, the lost side is going to be the hot side. And it looks like here that's going to be the aluminum. So I'm just going to make a little note for myself. The aluminum is the hot side. The thing that's going to gain energy is whatever started out cold. That's going to be the water side. So we've got a negative mc delta T equals a positive mc delta T. And let's plug some numbers in. Catch those masses. Remember, it has to be in kilograms. So it's negative 0.42 kilograms times the specific heat of aluminum, which is 903. Delta T is final temperature, which we don't know, minus the initial temperature, which I do know. I was given that for the aluminum. It started at 85. Equals, now over on that other side, we've got the water information. 200 grams, 0.2, times specific heat is 4180, multiplied by delta T, which is final temperature. I don't know what that is, but I do know what it started at. That was 15. Now notice the specific heats are different. 903 and 4180. Can't cancel them out then. That only works if you're going to have two of the same material mixed together. Here it's different materials mixed together, so you can't cancel anything. Now from here, what you're probably going to want to do algebraically is combine these two numbers. This is where things get a little bit slow just in terms of the number crunching. Let's combine those quickly. Negative 0.42 times 903 is negative 379.26. Times TF minus 85. And then we want to combine the 0.2 and the 4180. 836. So this is a little bit tedious now, but it's not hard. Just time consuming. So we end up with those values, and now you can distribute into the brackets and then start collecting all your like terms. So again, I'm going to pause the video here for a moment, just do that number crunching, and I'll throw it up on the screen. So there's what we end up with after distributing into the brackets. And now we can go ahead, we can start collecting, oops, I missed a TF in there. We can start collecting all of our like terms. So we're going to add 379.26 TF to both sides. And again, in the interest of space, I'm going to add this 12,540 to the other side. So that takes me to there. Hopefully those numbers match what you've got. Divide both sides by 1215.26. And I come up with a final temperature of 36.8 degrees Celsius. There you go. So again, if you just sort of step back, you look at this page, you're going to go, holy cow, there's a lot going on. But really, I think if you can get to this step right here, then from there, it's just some tedious calculator stuff, right? It really is those first few lines, getting things set up, getting the negative on the right side. Well, I should say the correct side of the equation. Figuring out your hot and cold. If you can do that, I don't think you'll have issues with these mixing questions at all. So give the homework a try from box 3. I'll cut it off there. Kind of long again. Sorry about that. Try that box number 3 practice. There are a couple of tricky questions in there, so don't feel bad if you get stuck. If you've got any questions about the lesson or the homework, hit me up in Zoom or fire me an email. or request your own little Zoom meeting, I am more than happy to help. Let's get this stuff sorted out. Have fun practicing with thermal energy.